Good morning, dear students. Today, let us discuss about process synchronization. This is the last chapter of Module 2. A cooperating process is one that can affect or be affected by other processes executing in the system. Cooperating processes can either directly share a logical address space, that is, both code and data, or be allowed to share the data only through files or messages. This is achieved through the use of threads, as we discussed in the previous chapter. And we also learned about independent processes. Independent processes are the processes which do not share the logical address space. The concurrent access to shared data may result in data inconsistency. So, in this chapter, we discuss various mechanisms to ensure the orderly execution of cooperating processes that share a logical address space so that data consistency is maintained. This is about the topics which we are going to discuss in this chapter. That is to introduce the critical section problem whose solutions can be used to ensure the consistency of shared data, then to present both software and hardware solutions of the critical section problem, then various uh, classical problems of process synchronization, and to explore several tools that are used to solve process synchronization problems. We have already seen that processes can execute concurrently or in parallel. So, the previous section introduced the role of process scheduling and described how the CPU scheduler switches rapidly between processes to provide concurrent execution. This means that one process may only partially complete execution before another process is scheduled. In fact, a process may be interrupted at any point in its instruction stream, and the processing core may be assigned to execute instructions of another process. Then we also studied about parallel execution, in which two instruction streams execute simultaneously on separate processing cores. So in this chapter, we study how concurrent or parallel execution can contribute to issues involving the integrity of data shared by several processes. Let us consider an example of how this can happen. We developed a model of system consisting of cooperating sequential processes or threads all running asynchronously and possibly sharing data. We illustrated this model with the producer consumer problem, which is representative of operating system. Producer is the process which is going to produce the item, and consumer is the process which is going to consume the items. Now we return to our consideration of bounded buffer. As we pointed out, our original solution allowed at most buffer size minus 1 items in the buffer at the same time. Suppose we want to modify the algorithm to remedy this deficiency. One possibility is to add an integer variable counter initialized to 0. Counter is incremented every time we add a new item to the buffer and is decremented every time we remove an item from the buffer. Now, how this incrementation and decrementation can be done? So, count plus plus can be incremented in machine languages as using temporary variables. Suppose counter value is assigned to register 1 initially. Now value of the register is incremented by 1. So register is equal to register plus 1. Then finally the value which is present in the register is assigned to count. This is about incrementation. Similarly, decrementation can be done by using another register, that is register 2. Initially it is assigned with the count value, then it is decremented by 1, and finally register 2 is assigned to count. So this is how count value can be incremented and decremented. Now let us consider the concurrent execution of counter plus plus and counter minus minus. which is equivalent to a sequential execution in which lower level statements presented previously are interleaved in some arbitrary order. One such interleaving is shown here. Now consider the value of count is equal to 5. Initial value of count which is equal to 5. Now assume that producer will execute the code. So producer means incrementing. So register 1 is equal to count. This is our first statement. Next time slice, producer will execute register 1 is equal to register 1 plus 1. So 5 plus 1, that is 6. Immediately after that, just assume that consumer will execute the code. So according to the consumer code, register 2 is equal to count. So register 2 is having the value of 5 and register 2 is decremented by 1. So value is 4. After these two statements, now assume producer will execute the code. So when producer will execute the code, register 1 value is assigned to the count, that is 6. Register 1 value is here, the 6 is assigned to count. Immediately after that, if consumer executes the code, register 2 value is assigned to the count. In register 2 we are having value 4, so 4 is assigned to count. Now just to consider the problem of this concurrent execution. According to producer, count value is 6. According to the consumer, count value is 4. But actually we took the counter value as 5. Notice that we have arrived at the incorrect state. Counter is equal to 4, indicating that 4 buffers are full when in fact 5 buffers are full. If we reverse the order of the statement at T4 and T5, we would arrive at the incorrect statement counter is equal to 6. That is, if we interchange T4 and T5, so first we have, if we execute consumer code, then count value is equal to 4, later count value is equal to 6. So the final outcome depends upon the order of the execution. We would arrive at this incorrect state because we allowed both the processors to manipulate the variable counter concurrently. A situation like this where several processes access and manipulate the same data concurrently and outcome of the execution depends on the particular order in which access takes place is called race condition. To guard against the race condition above, we need to ensure that only one process at a time can be manipulating the variable counter. To make such a guarantee, we require that processes be synchronized in some way. If we apply this concept to our real world, consider running race. Initially, we don't know who will be the winner. Who will run fast will be the winner. So initially, we don't know the final outcome of the race. Finally, we will come to know the result. That is called as race condition. Now let us discuss about critical section problem, a very important problem with respect to cooperating processes. We begin our consideration of process synchronization by discussing the critical section problem. Consider a system consisting of n processes P0, P1, P2 up to Pn minus 1. Okay? Many number of processes we are having. Each process has a segment of code called critical section, in which the process may be changing common variables, updating a table, writing a file and so on, where very important modification is going to be happen, which is called as critical section. Important feature of the system is that when one process is executing in its critical section, no other process is allowed to execute in its critical section. That is, no two processes are executing in their critical section at the same time. The critical section problem is to design a protocol that the processes can use to cooperate. Each process must request permission to enter its critical section. The section of the code implementing this request is entry section. So entry section is the section where request is made. The critical section may be followed by an exit section. means after executing the code in the critical section, then it has to exit. That is exit section. Remaining code is called remainder section. So the general structure of a typical process PI is shown in the next slide. So this is the general structure of process PI. As I told you earlier, there are 4 different sections. First one is entry section, where the request is made to enter into the critical section. If it is satisfied, enter into the critical section, where changing the common variables, updating a table or writing a file, such things can happen. Then after that, enter into the exit section, where the process is going to exit from the critical section, and finally remainder section. Now let us consider a solution to this critical section problem. Actually, there are three requirements, and students, please consider this as very important topic. What is critical section problem and what are the solution to the critical section problem? There are 3 requirements. What are those? Mutual exclusion, progress and bounded waiting. Let me explain one by one. First condition is mutual exclusion. Means if a process PI is executing in its critical section, then no other processes can be executing in their critical section. Understood? No? If one process is in the critical section, then no other process can enter into the critical section. Now just to compare this to our real world example, a class. Okay, for example, your class is the critical section, and faculty handling the class is the resource. If one faculty is taking the class, no other faculty can enter into the class. That is mutual exclusion. At a time, any one faculty can engage the class. Next one is progress. If no process is executing in its critical section and there exist some processes that wish to enter their critical section, then the selection of the processes that will enter the critical section next cannot be postponed indefinitely. That is, only those processes that are not executing in their remainder section can participate in the decision. Okay, for example, your classroom is free, that is no faculty is engaging the class, and there exist some other faculties, those who wish to take the class. Okay, consider that scenario. Class is free, no one is engaging, and some other faculties are eager to enter your class. Okay, that is the situation. Then who will enter? There is selection of the processes that will enter the critical section next cannot be postponed indefinitely. If the class is free, then another faculty can enter into the class. So that decision must be taken as soon as possible. Who will enter? There is one restriction. Only those faculties that are not just completed their class. I mean, consider that first hour is over. Then who can enter or who can engage the second hour class? The faculty who was not taking the class for you first hour can engage. That is the main important thing behind progress. Last one is about bounded waiting. A bound must exist on the number of times that other processes are allowed to enter their critical section after a process has made a request to enter its critical section and before that request is granted. That is, number of times that a process can enter into the critical section must exist. Indefinitely, just one process cannot enter into the critical section and cannot execute for many number of times. So there exists a limitation. So these are the 3 requirements for a critical section problem. Now we will consider one software based solution for the critical section problem, that is called as Peterson solution. We have software solution as well as hardware solution. Hardware solution let us see later after considering this. So what does this indicate? Peterson solution. So it is a software based solution to the critical section problem because the way modern computer architectures perform basic machine language instructions such as load and store, there are no guarantees that Peterson solution will work correctly on such architectures. However, we present the solution because it provides a good algorithmic description of solving the critical section problem and illustrates some of the complexities involved in designing software that addresses the requirements of mutual exclusion, progress and bounded waiting. So Peterson's solution is restricted to two processes that alternate execution between their critical sections and remainder sections. Just two processes, P0 and P1, or PI and PJ we will consider. Peterson's solution requires two processors share two variables. What are the two variables? That is int turn and a boolean value flag 2. So variable turn indicates whose turn it is to enter the critical section. Okay, turn indicates who will enter into the critical section. Then the flag array is used to indicate if a process is ready to enter the critical section. That means if flag of I is equal to true implies that process Pi is ready. If flag of j is equal to true indicates process Pj is ready. Okay. Turn indicates whose turn it is to enter into the critical section and flag indicates who is ready to enter into the critical section. Now let us see the code. This is the algorithm for Peterson's solution. Here there is infinite loop do while the condition is true, this is going to execute. Initially flag of I is equal to true. To enter into the critical section, the process Pi first sets flag of I is equal to true and then sets turn to the value j. Okay, turn is equal to j, thereby asserting that if the other process wishes to enter the critical section, it can do so. If both processes try to enter the critical section same time, turn will be set to both I and j at the same time. But only one of these assignments will last, the other will occur but will be overwritten immediately. So the eventual value of turn determines which of the two processes is allowed to enter its critical section first. While flag of j means flag of j is equal to true and turn is equal to j. If both conditions are true, then process Pj is in the critical section, so no other process can enter. The semicolon means do nothing. Otherwise, if this is not true means any one condition is false, then that particular process can enter into the critical section. After executing the code in the critical section, flag of that particular process is made as false. Then it will allow other process to enter into the critical section. This is about process P0 and this is about process P1. Students, please try to trace this code. This is homework for you. Now, we prove that this solution is correct. We need to show that first condition, mutual exclusion is preserved. Second condition, see here, first one, mutual exclusion should be preserved. Second, the progress requirements must be satisfied. And third one, bounded waiting requirement is met. So to prove property 1, we note that each PI enters its critical section only if either flag of j is equal to false or turn is equal to I. Okay, understood? Any one condition out of these two, any one is true, then only it can enter, PI can enter. Also note that if both processes can be executing in their critical section at the same time, then flag of 0 is equal to flag of 1 is equal to true. Okay, understood? No, if both are there in the critical section means both these two flags are true, flag of I as well as flag of j, both are true, but it is not possible. It is a boolean value, saying any one value can be true. These two observations imply that P0 and P1 could not have successfully executed their while statement at about the same time, since the value of turn can be either 0 or 1 but cannot be both. Hence, one of the processors, say Pj, must have successfully executed the while statement, whereas Pi had to execute at least one additional statement, turn is equal to j. However, at that time, flag of j is equal to true and turn is equal to j, and this condition will persist as long as pj is in critical section. As a result, mutual exclusion is preserved. Now we have to prove properties 2 and 3. We note that a process Pi can be prevented from entering the critical section only if it is stuck in the while loop with the condition flag of j is equal to true and turn is equal to j. This loop is the only one possible. If Pj is not ready to enter the critical section, then flag of j is equal to false and Pi can enter its critical section. If Pj has set the flag j to true and is also executing in its while statement, then either turn is equal to I or turn is equal to j. If turn is equal to I, then Pi will enter the critical section. If turn is equal to j, then Pj will enter the critical section. However, once Pj exits its critical section, it will reset the flag of j to false, allowing Pi to enter its critical section. If Pj resets the flag of j to true, it must also set turn to I. Thus, since Pi does not change the value of the variable turn while executing the while statement, Pi will enter the critical section, that is progress, after at most one entry by Pj, that is bounded waiting. In this way, we can prove that this code is correct, that is Peterson's solution is correctly working for critical section problem. First three and all three conditions, mutual exclusion, progress and bounded waiting, are met. So in the previous section we have studied about a software solution. Now coming to the hardware solution. We have just described Peterson's solution, which is a software-based solution to the critical section problem. However, as I mentioned earlier, software-based solutions such as Peterson's are not guaranteed to work on modern computer architectures. In the following discussions, we explore several more solutions to the critical section problem using techniques ranging from hardware to software-based APIs available to both kernel developers and application programmers. All these solutions are based on the premise of locking, that is, protecting critical regions through the use of locks. As we shall see, the design of such locks can be quite sophisticated. Go through this code. This is called as mutex locks. There is a do while loop, as I said earlier. Operating system designers build software tools to solve the critical section problem. The simplest of these tools is mutex locks. We use the mutex lock to protect the critical regions and thus prevent race condition. That is, a process must acquire a lock before entering the critical section and it releases the lock when it exits the critical section. The acquire function acquires the lock and the release function releases the lock. Next, let us discuss about a tool, synchronization tool called as Semaphore, and this is also very important topic in synchronization chapter. Mutex locks, as we mentioned earlier, are generally considered the simplest of synchronization tools, that is acquiring lock and releasing the lock. In this section, we examine a more robust tool that can behave similarly to a mutex lock but can also provide more sophisticated ways for the processors to synchronize their activities. A semaphore yes is an integer variable that, apart from initialization, is accessed only through standard atomic operations wait and signal. The wait operation is called as P, and which is for decrementation, and signal operation is called as V, which is incrementation. That is, we will consider this semaphore integer value as the resource count. Resource is a very important thing to execute any program or process. For example, CPU is the resource, memory cycle is the resource, keyboard is the resource for taking the input, monitor is the resource for displaying the output, etc. So here we will consider the semaphore count integer value as the number of resources. Now how these two functions wait and signals are implemented. See, wait function is implemented like this. Wait of s, where s is the integer count, while s is less than or equal to 0. Less than or equal to 0 means negative. Negative means there are no availability of resources. If there is no availability of resources, then there is a semicolon, no operation. Means without having any resource, we cannot execute a program. Otherwise, consider this s minus minus in the next statement. Okay, next line. Otherwise, if this is not true, this is not true means s value is positive. If s value is positive, we have sufficient number of resources. So out of sufficient number of resources, one resource has been taken out, so s minus minus. Okay, so consider s value as some 10. If we have 10 resources, one resource is already allocated to execute one program, so after execution we have 9 resources, so s minus minus, that is decrement. Okay, I think you understood this code, wait operation. Next, what is signal operation? Signal is like releasing the resource to the operating system. After entering into the critical section, a process after the execution, complete execution of the process, then it has to return its resource to the operating system by calling signal function. Is here s plus plus, returning the resource to the operating system where the count increments. Suppose we have 10 resources, then after releasing the resource to the OS, then we have 11. Now the types of semaphores. We have two types of semaphores. Operating systems distinguish between counting and binary semaphores. These are the two types. One is counting semaphore, another one is binary semaphore. The value of a counting semaphore can range over an unrestricted domain. The value of binary semaphore can range only between 0 and 1. So in the counting semaphore, control access to a given resource consisting of a finite number of instances. Thus, binary semaphores behave similarly to mutex lock. In fact, on systems that do not provide mutex lock, binary semaphores can be used instead of providing mutual exclusion. This is the code for mutual exclusion. Semaphore mutex. Okay, mutex is the name of the semaphore. First call wait function. Wait function acquiring the resource, enter into the critical section. After executing the code in the critical section called signal function, releasing the resource to the operating system, then enter into the reminder section until the condition is true. So counting semaphores can be used to control the access to a given resource consisting of a finite number of instances. The semaphore is initialized to the number of resources available. For each process that wishes to use a resource performs a wait operation on the semaphore, thereby decrementing the count. When a process releases the resource, it performs a signal operation, that is incrementing the count. When the count for the semaphore goes to 0, all resources are being used. After that, the processes that wish to use the resource will block until the count becomes greater than 0. Next is a small topic about deadlocks and starvation. The implementation of semaphore with their waiting queue may result in a situation where two or more processes are waiting indefinitely for an event that can be caused only by one of the waiting processes. The event in question is the execution of the signal operation. Once such a state is reached, these processes are said to be deadlocked. That is, two or more processes are waiting indefinitely for an event that can be caused by only one of the waiting processes. You consider this code. Let S and Q be the two semaphores initialized to 1. Initialized to 1 means resource is available. P0 and P1 are the two processes. P naught calls the wait function and signal function in this sequence: wait of S, wait of Q, then after some code, signal of S and signal of Q. At the same time, P1 calls the functions in this order: wait of Q, wait of S, signal of Q and signal of S. So how exactly deadlock happens over here? P0 is waiting for resource yes, but that resource yes is available only when this P1 called signal of yes. Okay, only when P1 calls signal of yes, then only P0 can get the resource yes. Similarly, P1 calls wait of Q. So means it is waiting for the resource Q. This can acquire the resource only when this process P0 calls signal of Q. The resource required by P0 is held by P1. The resource which is required P1 is held by P0. So as a result, P0 cannot execute, P1 also cannot be executed. This particular situation is called as deadlock. Indefinitely they are waiting for the resource which are held by another process. Another one is starvation, or it is also called as indefinite blocking. It is a situation in which processes wait indefinitely within the semaphore. It may occur if we remove the processes from the list associated with the semaphore in last in first out order. This is about deadlock and starvation. So we have studied only important topics over here, like critical section problem, requirements for the critical section problem, a software based solution called as Peterson solution, and hardware solution using mutex locks, as well as semaphore and its implementation. So in the next video, let us discuss about classical problems of synchronization. Thank you students. Happy learning.